Hi, my name is Tieho. So today I'm going to do our Linux lessons differently. One of the friend of mine actually advised me that I should maybe consider making short videos than to make one long video. If you check my videos, my previous videos, you'll see that they're about one hour, 1 hour 30 minutes long. So a friend of mine actually advised that maybe I should consider changing the style and making maybe 5-10 minutes videos, and they become more interesting and people will actually watch them. So today that's what I'm going to do. That's what I'll be doing today. So today I just want us to talk about improving the performance of your application. I've seen many engineers and system administrators, they actually ignore this part, and it's very important. You need to know how to improve the performance of your application. The only way you can improve the performance of your application is when you understand your application. You need to understand how your application works. You need to understand, is it doing sequential reads to your data? Is it doing random reads? Is it throughput orientated? Is it IO orientated application? And with all those questions that you need to answer, then you'll be able to fine-tune your operating system to better serve your application. And so with that in mind, I want us now to talk about improving, of course, your application performance. So you'd understand that everything that needs to be processed by CPU, it goes through memory, right? There is nothing that gets processed without being in memory. A CPU cannot process anything that is sitting on the disk, the actual disk. It has to be running in memory. It has to be loaded in memory. And memory is somehow a sort of one kind of storage that we have. And memory is way faster than a disk, but there are sort of all kind of storage. They are different, but there are types of storage. The other one is it's a volatile, the other one is non-volatile. So the disk is non-volatile, meaning if it happens that you switch off the machine or something happens and it instantly shuts down, you will not lose anything that is on your non-volatile storage. That is your disk, your volume. Anything that was loaded in your volatile storage, your RAM, will be lost. However, there are some serious advantages of having your data in RAM, in memory, because memory is way faster than disk. Now, engineers, they've noticed that anything that is in memory is faster than disk, so they try by all means to get their data running, or not running, being in memory, in a volatile storage, to improve the performance of the application. Hence, they came with things like Redis and Memcache to try to improve the performance of the application, because they then run most of the stuff in memory than to be sitting in your disk. And understanding how your application works, you can actually fine-tune your operating system Linux to be able to handle all those things. So because we noticed that memory is fast, we kept on then the adding different types of memory to improve performance. So why different types of memory? The more memory is closer to the CPU, the faster it becomes, right? And then that then ended up having engineers coming up with ways of getting closer and closer to the CPU. But here's the thing. The closer you get to the CPU, the faster the CPU gets to memory, to that kind of memory, of course. However, you improve the speed at the cost of size. The closer you get to the CPU, the smaller that memory becomes. Okay? So, the speed increases, the size decreases. So let's talk about this kind of memories. We have a CPU. Next to this CPU, we have a registry or a register. A register is part of the processor. Because it's a part of processor, it's extremely fast. But remember that even though it's extremely fast, it's very, very slow. So we are talking about, not extremely slow, sorry. It's extremely small, but extremely fast. The size of registers, they're about 1,000 bytes. They don't usually go beyond 1,000 bytes. But when it comes to speed, it's a real deal. It can go to about 300 picoseconds. And that's very fast. 300 picoseconds. If you have never heard of a PN, seconds, then you need to research about it. It's about 1 trillion of a second. 1 trillion of a second. So that's how fast it becomes. However, the size is about 1,000 bytes. It cannot go beyond that. And let's talk about the next storage that comes after that. After that, usually what comes will be your cache memory. We call them cache memory or CPU caches. CPU caches. We have got 3 CPU caches. We have got L1, L2, and L3, right? L1 is closer to the CPU and it will be faster than the L2, and L2 will be faster than L3, okay? But as you go down, the size increases, the speed decreases. So the L1, it can go about 64 kilobyte. It can be around 64 kilobyte. And we are talking about 1 nanosecond. CPU to be able to get to the registry one, to get to the CPU cache L1, it takes about 1 nanosecond. Remember, to get to the CPU register, it takes about 300 picoseconds. And we move from picoseconds to nanoseconds. And then we move to L2 cache. The L2 cache, the size can be around 256 kilobyte, right? But the speed now, we start seeing it getting slower. Remember, L1 it's 1 nanoseconds, about 1 nanoseconds. This one, it's between 3 and 10 nanoseconds. Then we go to L3 and the size become a little bit bigger. We have got about 2 to 4 megabytes, but the speed moves from between 10 and 20 nanoseconds, right? And remember that the CPU clock speed plays a role as well here. That's why I'm giving you ranges to say between 10 and 20 nanoseconds, because the speed of the CPU will play a role as well on how fast is the CPU. Then we go to RAM. Nowadays the RAM, I think they start from 4 gigabytes up to 16 gig, 1 DIMM. And to get to that, for CPU to get to that, it takes about 50 to 100 nanoseconds. So you see that even though we see RAM memory as fast, it cannot be compared to cache memory, the CPU cache, the L1, L2, and L3. And L1, L2, and L3 cannot be compared to the CPU register. Okay? And now, from RAM, we then go to swap or the disk space, the disk storage. And now things get even more and more and more slower, but the size becomes big. We are talking about 4 gig to 16 terabyte in size. However, the speed, it can go from 5 to 10 milliseconds. Remember that we moved from picoseconds to nanoseconds. Now we are on milliseconds. So understanding this is very, very important for you to be able to improve the performance of your application. Very, very important to understand all this kind of memory and storage. So if you understand this, your aim as an application administrator or developer, you want to run away from storage as much as possible, and if possible, move some of the stuff from RAM into L1, L2, L3 cache. Now, let's talk about trying to run away from swap or storage, right? It's very slow, 5 to 10 milliseconds. It's a very large number. I'm just gonna recommend few things to you, and you'll see that you can start improving the performance of your application. So the way you can improve these things, there are 2 ways. Let's talk about the application, the read operations. If you want to improve the reads of your application, you can do something interesting on your Linux platform to try to enhance or help the application when it comes to read operations. But before you can do that, you need to understand how your application works. If your application is doing sequential reads, meaning on the block, this is a block storage, it's reading one block after another, and they are sequential, one after the other, one after the other. Then you can then sort of help the application to stop going to the slow disk and putting things in memory before they're even required by the application. How so? Because you see that the pattern, you can see the pattern that it's sequential, one block after the other. You can read a block of information before it's required by the application. By the time it's required, it's now being found in the cache, in the memory cache. Remember, we've got CPU cache and memory cache. Don't confuse the two. So the memory cache that we're talking about, all the reads that are happening, all the information that is required usually is fetched from the slow disk and it's in the memory, and that information is saved in the cache. It improves the reads of the operating system and applications. And we've got another part of memory that is called buffer. All the writes that are issued by the application or operating system, they are buffered in the memory. Then later, they can be written to the slow disk. We'll get to that. Now that we know that the reads are sequential, what we can do what we call read ahead or fetch, or what we call a prefetch. It depends what operating system you are working on. I'm from Unix. We used to call it prefetch, but on Linux it's called read ahead. So I'm going to show you how you can set a read ahead on Linux. Let's see. I'm on my CentOS 7 here, and let me just make sure. Oh, sorry, I made a mistake there. I need cat. So yes, I'm running CentOS 7, and now let's see what I'm talking about. The command that I want us to talk about is called block dev. If you check the block dev commands here, you will see that we want to let's first see if we have any read aheads configured in this operating system. So we'll say block dev read ahead. For which device? We need to specify a device, okay? The one that will be doing a prefetch or read ahead from. So we want to check first which is set up here. So it shows us that the read ahead configured in this operating system is 8192 blocks, 8192 blocks. If you check the it's actually 8192 sectors, okay, of block. It's fine. So what you need to do here, you need to convert these sectors into kilobytes or megabytes. For us to get that, you need to divide this number by 2 to get to kilobytes. So you'll take your calculator and convert that by 2, and that is 4096 kilobytes. And you convert this into megabytes, you will divide it by 1024, and then we know that our read ahead in this operating system is 4 megabytes. What if you want to change a read ahead? So before I even change it, it means if the reads are sequential, the operating system can help by reading ahead 4 megabytes information before it's even requested from the slow disk, and it's prefetched and loaded to the cache, to the memory, right? As the application issues the read operation to read the next sector of information, it then finds it in memory. And now, because RAM is way faster than a disk, then we start seeing improvements in our application. Now, we call this when the data that is required, that is read from memory, not from the disk. We then say we have cache hits because the read operation that was issued by the application was fulfilled in a RAM, not in disk, and we call that cache hit. If the information that is required is not in RAM and it has to be read from disk, we say we have a cache miss. The other one is cache hit, the other one is cache miss. Cache miss is expensive for the application. How so? Because the application becomes slow because it has to wait for the read to be fetched from the slow form of storage, of which is a volume or disk. If you are working in AWS stuff, we call them EBS volumes. So you try by all means to run away from the disk. Now, we have seen that, okay, we've got 4 megabytes of read ahead. If you want to increase it, then you can use set, let's see here, let's see here. You can use this command to set read ahead and put sectors there. So you know that if you want to make it 8 megabyte, you convert 8 megabyte to kilobytes and you multiply by 2, right? Then you take that sectors and you put them here. So it will be 892 multiplied by 2, like so. Multiply by 2, and you take this number, then you say block def and then set read ahead, and that becomes our disk that we want to apply. And now when we check again read ahead for that disk, this is the new number, and now you've got 8 megabytes of read ahead. Okay, so when you have cache miss, it triggers what we call major fault. And when you have your data is in cache, we have what you call minor faults. Minor faults are not expensive in terms of performance, but major faults are expensive in terms of performance. If you want to know about major faults and minor faults, I will get deep into them in the next lesson. But you can actually install a command called time. There is a time command that comes with the operating system, but that time command is not going to give you the information that we require in this example. So you then going to use the time that you're going to use. It's in user bin and it's called time. And for example, if I want to maybe, let's say, list things in my directory here, and want to see some information after that, you can use time before you run the command, and after listing or giving the output of the command that you run here, it will give you the statistics here down here. You will see that here we have major faults and minor faults here, and you see that we don't have major faults, we only have 406 minor faults. It means in terms of performance, this command was very quick to run because it didn't have to go to the slow form of storage, of which is disk. Okay, so you can use this command to check all those kind of things. Fine. Now let's move to another thing. We just improved the reads of the sequential, right? Let's talk about writes. We've got two types of writes. We've got synchronous, asynchronous write operation and synchronous write operation. Asynchronous write operations, it's when the application issues the write operation, the operating system, what it does then, it then stores that information that needs to be written to the disk into the memory, a part of memory called buffer, and it then sends a response back to the application to say the data has been written. Even though it's lying to the application, the data is still in memory, not in the actual storage. remember that we said RAM is a volatile form of storage, and the volumes, the disk, are non-volatile form of storage. So now the application, the operating system lies to the application to say the data is written, and the application does not have to wait for this data to be written to the slow form of storage. It then continues doing what it was doing. But if you do synchronous writes, the writes will go directly to the slow form of storage, right? And it will have to wait until it gets a response back to say the data has been written. Hence, there will be some performance degradation there. It could be something noticeable or something that is not that noticeable. It depends. And again, it depends. The slow form of storage is this SSD, of which is much better than other form of storage. So it depends on all those other things. And so you need to know then, is my application doing more writes or doing more reads? That kind of information is very important for performance tuning. So now we have, so if you want to improve writes, you can then configure asynchronous writes, right? But you need to know that it can be risky, because if it happens that that server all of a sudden goes down, all the things that are in memory that are not written in the slow form of storage, they will be lost. So you have to be very, very, very careful with asynchronous writes. I know the other database vendors, they don't want such things, they don't do asynchronous because database is very sensitive. They don't want to lose any data. So be very careful when you do all these things. They can be nice, but be very, very careful. So another thing that you can take into consideration would be, if you want to improve writes, you can then have what you call a mirror rate. Rate, if I'm not mistaken, it's rate 1. You can do rate 1, mirror your disks. That will improve the writes operations of your disk, because it has got 2 disks. Actually, not mirror, sorry. You'll have to do striping. That should be rate 5, if I'm not mistaken. You'll have to do striping to more than 1 disk. So if you have got 3 disks or 4 disks, when it writes, then it writes across 4 disks, and that improves the writes of the application. But if you do that, you must know that in terms of reads, you will see some degradation, because when the application now has to read, it has to now try to read data across 4 disks. You can imagine if some information that is required is on disk 1, that are on disk 2. So there can be some serious degradation in terms of read operations, but in terms of write operations, it will be very fast. So make decisions. Is your application write intensive or read intensive? All those information will help you to fine-tune your application. With that, thank you very much.